Hello physicists, welcome to our April 28th edition of physics, our very last physics video. So sad. Alright, but thank God many of you will see me again next semester. Now, one thing I want to bring to your attention, because we are right at the end, is that I still have this offer to you that if 90% of you fill out your course evaluations, I will personally add 5% to everyone's exam score. Let's see, how are we doing right now? As of midnight last night, there were 12 of you out of 21 who had filled this out. As of now, I believe there are 13, but to get 90%, we need 19. So there are 6 of you who need to be heroes now. Step up to the plate and help all of your fellow classmates. Now, because this is our last day in physics, I thought it might be worthwhile to hit a point. I know I mentioned this earlier, but it comes again because it's the end of the semester. And so the point I want to make is, I know that it feels like you've mastered most of physics. And I don't want to denigrate any of your achievement in having gotten this far, because getting through Physics 1 is no small feat, and I very much appreciate all the work that everyone who has followed along this far has done. But if you wanted to go ahead and ask, pro physicists what their picture of the world is, basically nothing that is in the first semester of physics is there. So we have, for gravity, you have all this general relativity stuff, but this is all in terms of space-time and the curvature of space-time and a stress-energy tensor and all of this stuff. That looks very different even from the Newtonian gravity that we got at the end of our semester this time. By the same token, in the other part of physics, which is basically electromagnetism to describe virtually everything in our everyday world, then there's the strong nuclear force, which you need to introduce to try to explain why the nuclei stick together in atoms, and then the weak nuclear force to understand why there's such a thing as radioactivity, why some of those nuclei decay. Now, that doesn't seem like it has a lot to do with the forces that we've talked about, like centripetal force, frictional forces, tension forces. Those are all basically electricity, but in a very different sort of language. And so I just want to at one time say, congratulations, you got done with your first course of physics, but then also just, hang on, we're not to the end yet. So we have a lot to learn next semester, and furthermore, even if you finish next semester, there's a lot more to be known. So there's a lot in this subject, and in fact, if you talk to cosmologists, most of them would tell you that these things, the standard model fermions and bosons of quantum field theory, and even the space-time curvature of general relativity only gets at about 5% of the normal stuff that's around us, and they infer the presence of dark energy and dark matter making up the other 95% of the energy density of the universe. Okay, well, let's push that aside. That's just a bit of advertisement. If you want to go further in that, I am always recruiting physics majors. Or at this point minors, but you can see where I'm going with this. Okay, so what are we going to do today? We are going to go ahead and review all of the stuff from Unit 3 that we haven't hit yet. So things like momentum conservation, our angular coordinates we did a little bit of, but we want to see how we can recast our F equals ma in terms of angular terms, talk a little bit about angular momentum, and then hit the last gravitation problems that we haven't covered yet that were on the review. Okay, so the first one that I want to hit is momentum conservation. So there was a question that I asked on test 3 that said, is it true that if you don't have outside forces on a system, that the total momentum of the system is 0? Now that turns out not to be true. Why is it? Well, consider this system right here. The mass times the velocity of a particle is its momentum. So if we have a before type of story here, the total system of my two balls, they can both have mass m, is already mv. So the total system has some momentum, and when the two balls, let's say we have a version of this story where there's an initial speed, and now they stick together, and the momentum is now 2m. These two balls are both of the same mass, I guess, and some v final. That v final would have to be smaller because the initial momentum equals the final momentum. Okay, so this would be an example of an inelastic collision. In this story, we couldn't use energy conservation because when objects stick together, they tend to heat up a bit. And so you could make a case, I think, that if you tracked the motion of every single little particle and added up the 1/2 mv squared, that you could come to something close to energy conservation. But if you just are worrying about this motion and then that motion, you definitely don't have energy conservation. You have to look a little deeper. So because of this, we introduced problems that I hear him calling combination problems, where part of the problem uses one kind of physical principle and another part of the problem uses another kind of physical principle. For instance, in this in the ballistic pendulum problem, you take a bullet, you shoot it into the pendulum, and then the pendulum goes up to some height, and you use that to infer the speed of the original bullet. And the story that you tell is as follows. At the moment the bullet hits the block, that sets the speed of the block. And the block and bullet system has the same momentum as the initial momentum of the bullet. So you get to use conservation of momentum in that part. Then the block begins to rise, and during the swing of that pendulum, you get to use energy conservation. So you're using momentum conservation for the first part, energy conservation for the second part of the problem. You're trying to suss out which physical principles are relevant to which part of the problem. So this brings us back to a problem that we ended our last video with. The problem of the roller coaster, which is one of your short answer questions, which, as I say, will be a exam question. So the part that we already went over, we said, let's say that you have this car is moving at some speed, and so it has some kinetic energy at the beginning, and it has also some gravitational potential energy at the beginning. And then it goes down, the kinetic energy is the gravitational potential energy is transferred into extra kinetic energy. Here now we're losing kinetic energy, gaining gravitational potential energy. And so you want the kinetic energy plus the potential energy at this first position to equal the kinetic energy plus the potential energy at the second one. Okay, so then we filled in 1/2 mv1 squared plus mgh1. So this is kinetic plus gravitational potential equals 1/2 mv2 squared plus mgh2. Okay, so that was the first part that we already went over. Now here's the second part. It says the car at the bottom of the second hill, car A hits another identical roller coaster car B, and the two stick together. How fast will they move together after their collision? All right, so I hope that you see relevant to what we were just talking about. In this second part of the problem, it's going to be momentum conservation, not energy conservation, that's relevant, because in this case, when you stick together, there can be some frictional forces, and you lose some of that energy as heat. However, to find the speed at the bottom, okay, you will need to use energy conservation. So your 1/2 mv1 squared plus mgh1, that's your energy at the top, should be the same as the energy at the bottom, 1/2 mv bottom squared. Okay, so that's your car right before it hits has some speed, and I'm calling that v bottom. Now then, so this is using energy conservation. And then next we're going to use momentum conservation. Okay, so how am I going to use momentum conservation? I'm going to have my momentum of the car A before it hits car B will be m v bottom. That's it. Then afterwards, the two cars are stuck together, and they're going to, so let's call this v bottom initial, for instance. And then afterwards, you're going to have the two masses that are going to stick together, and then that will be your v bottom final. Okay, so you are eventually going to report this. Now, as you can see, if you divide both sides by 2m, essentially this v bottom final is going to be half as big as the v bottom initial. All right, so that does not, it's not an elastic collision, it's inelastic, they're sticking together, but we got to use our momentum conservation to allow us to figure out how fast those two are going together at the end. Okay, so great. The other part of the momentum stuff that we covered quite a bit was the impulse momentum theorem, where your change in momentum is due to your impulse, which is the net force times the amount of time. And we said just as applied work changes the kinetic energy, applied impulse changes the momentum. I don't have a lot of stuff on the exam on that, so I'm going to kind of rush over that. Okay, so after we did that, then we went on to angular coordinates, which, as I've said umpteen times by now, are useful because stuff nearer the axis of rotation is moving more slowly than stuff that is farther from the axis of rotation. And this allows you to use angular position, angular velocity, and angular acceleration. And this allows you to talk about different parts of a spinning object in terms of the same coordinate. Then, as we discussed the other day, we were able to have sort of a substitution code where we would replace all of our positions with angular positions, our velocities with angular velocities, our times, well, time is the same, our linear acceleration with angular acceleration, and so on. And we could then use our model that we spent a lot of time developing, the constant acceleration model. We could use that in terms of spinning objects. So just to remind you, I think I've already done this on a different video, but if you have your theta, you can find your omega by taking the derivative of your theta with respect to t. So this is going from position to velocity. And if you want to go from velocity to acceleration, you again can take your derivative of your velocity with respect to time, gives you your acceleration. And in this problem, you'll recall that it's asking about average velocity. So average velocity is just your total displacement, here angular displacement over total time. Your average acceleration is just your change in your angular velocity over your change in time. Now, one way that this is different from what we did before, because remember, we already had talked about going around in a circle. There is a component of that acceleration that's already towards the center of the circle. That requires a force. That requires a net force, F equals ma type of net force, where the acceleration can be found using your v squared over r. But now we're trying to think about what if you have a force that's causing you to spin more quickly. So you're not just going around a circle at a constant speed, you could be speeding up or slowing down. Well, that acceleration is not in the direction towards the center of the circle, that is in the direction tangential to the circle. And so if you wanted to find a net force, you'd have to add together these components as a vector, take the magnitude of that and multiply it by the little piece of mass. Now, okay. Now, as I've already alluded to, the principal difficulty with all of this spinning stuff is that the parts of an object that are closer to the axis of rotation are moving more slowly than the objects that are farther away. And so what we do, because we want to write things like kinetic energy, kinetic energy equals 1/2 mv squared, we would like to have some quantity that looks like that kinetic energy, but it's in terms of something more convenient, instead of having to add up the little mass times v squared of every single point on our disk, for instance. And so the way that we do it is by introducing this quantity called the moment of inertia, and it essentially weights the points that are farther out on the disk more heavily than the masses that are closer to the center. Why are we doing that? Well, because if you have an object that is spinning, for instance, and you want to know the kinetic energy, the objects on the outside have more kinetic energy. So they contribute more to this factor I. So then we were able to write our kinetic energy in terms of I times omega squared. Remember, so now this looks like 1/2 mv squared. It means a little bit different thing, but essentially it comes from the same place. You're taking every little bit of mass in that disk and adding it up, timesing it times v squared, and we're writing it in this different form. Now, that moment of inertia depends not only on the geometry of the material, it also depends on the way that you're spinning it. So for instance, here's an example. You have 1/2 mr squared. If you have your solid disk and you're spinning it around the center. On the other hand, here you see it's quite different if you spin it. So that's me spinning my pen like this versus spinning my pen like this. So when I spin it around the other way, here it's 1/4 mr squared plus 1/12 ml squared. So that's quite different, and you need to be aware of both the geometry and the way that you're spinning it, the axis of the rotation. So in terms of how well you need to know this stuff, it's to this extent. This was a question I put on your last review, but it's a good one. The moment of inertia comes from just adding up the little moment of inertia of every piece of mass in your object. So in this case, it depends on how far you are from the axis of rotation. How far each mass is from the axis of rotation. So if I have 1, 2, 3, and 4, for instance, my moment of inertia would be the moment of inertia from 1 plus the moment of inertia from 2 plus the moment of inertia from 3 plus the moment of inertia from 4. This is right on the axis, so that would be 0 plus, now I've got to take my mass times r squared, so m times a squared for 2 plus m times a squared for 3 plus m times, and this is 2a away from the axis of rotation, so that would be 2a squared. Okay, so this is 1, 2, 3, 4, 5, 6, 6m a squared. I will let you put in the numbers and finish that one up. Okay, so the nice thing about this type of way of writing the kinetic energy is that there's another use for this quantity, the moment of inertia. And that is that it allows us to rewrite F equals ma in a new form. And that is torque equals moment of inertia times angular acceleration. Now, there's something a little bit different about this because torque is r cross F. It has units of basically energy, force times distance, and it's giving us the force that I'm picking out is the amount of force that's in the direction of the tangent. So in the direction tangent to the circle, in terms of this, if I drew a R and an F, so there's my R, there's my F, and this was the theta, or the phi between them, then my torque would be magnitude of R times magnitude of F times sine of that angle. But if they are perpendicular, it's just R times F. And just to let you in on a secret, that's how they're going to be in the exam. Okay, so just to look at the easiest possible example of this, we're going to have torque equals I times alpha. Okay, so in this case, it says a disk with a rotational inertia of 2 kilograms per meter times meter squared. 2 kilograms meter squared times alpha equals rotates on a frictionless fixed axis perpendicular to the disk faces and through its center. A force of 5 newtons is applied tangentially to the rim. Okay, so this is just going to be my R times F because we're applying the force like this. It's just perpendicular. So this angle, it's a right angle. So my R and my F are going to be, well, radius 0.4 meters, 0.40 meters. My F is going to be 5 newtons equals 2 kilograms meters squared times alpha. Okay, I'll let you finish that one. All right, then we did all of our extra stuff in terms of angular coordinates. So we did work and energy. So work is instead of being force times distance, it's torque times angular displacement. In terms of rotational work energy theorem, it was just kinetic energy. Now we're writing that in terms of I and omega squared. The change in the kinetic energy is the amount of work that you put in. The amount of power in linear terms was written as force times the velocity. Here it's torque times the angular velocity. So you can see how all of this stuff is kind of carrying over very directly from the linear to the angular context. Now, the last one of these angular issues that I want to highlight is that of angular momentum conservation. Just like with linear momentum, if you have a closed system, you can have objects that are interacting with each other, but if they don't have an outside force on them, the total angular momentum before is the total angular momentum afterwards. So the moment of inertia of your system times the angular speed of that system before equals the moment of inertia of the system times the angular speed afterwards. So in this case, the moment of inertia is adding up all of your masses and taking r, the distance to the axis of rotation, squared. In this case, when he pulls his arms in, the r gets smaller for these two masses, and so the I gets smaller. But if your I gets smaller, your omega has to get bigger. So I gave you one problem on your review that was like this. It says, when a woman on a frictionless rotating turntable extends her arms, okay, so she's going like this, there she is, she's going to be like this at the end. Okay, now the I initial times omega initial would give you her initial angular momentum. If you have momentum conservation, that means her I final times omega final has to be the same. Now in this case, her moment of inertia goes up because her arms get farther away from the axis of rotation. So this goes up. This would go down, she would get slower, but on the other hand, her angular momentum must stay the same. That's part of this story, is that this I omega is the same before and afterwards. Okay, so I increases, omega decreases, angular momentum remains the same. Now, to drive this point home, how we can combine different physical principles in the same problem, I am going to essentially put the same problem that I put on your last test on the exam. And we haven't discussed this problem yet, but I want to go over it in detail today so that hopefully you're not confused about it. And remember, you have your last assignment is you're going to be handing me your test review at the time of the exam. So please be ready for that. All right, so it says, a merry-go-round has a radius of 2 meters and a rotational inertia of 500 kilograms times meters squared about its center axis of rotation. Okay, so we start out with this merry-go-round. Okay, it's got some axis of rotation, and we're told that this initial is going to be just 500 kilograms times meters squared. Now I'd ask, what would be the rotational inertia of the merry-go-round with a 15-kilogram child standing on a position on its edge? Okay, so this is 2 meters. Remember, all you're doing to get your moment of inertia is taking the mass of each part of the object times the distance to the axis of rotation squared. So if you want to find it with the kid, you would take the I naught, that would be your 500 kilogram times meter squared, and here you have a mass of the kid, and you have the radius. So the mass of the kid is 15 kilograms, so you'd have plus 15 kilograms times 2 meters squared. Okay, so 15 times 2 would give you 60, so the overall you should get a moment of inertia of 560 kilograms times meter squared. Now, for part B of it, it says, if a constant force of 600 newtons is applied at the outer radius for 3 seconds, with what angular velocity would the merry-go-round with a child on it spin at the end of the push? Okay, well this is just a torque equals I times angular velocity, and then angular acceleration, and then once we have that angular acceleration, we can go ahead and find the final angular velocity. Okay, so just to flesh that out a little bit, we're applying that 600 newtons at the outer edge of the merry-go-round. We've been told this is 2 meters. So my torque is going to be force, or it's going to be R times F, and if they're perpendicular, it's just R times F. So that's going to be 1,200 Newton meters. My torque equals I times alpha. So this would give me 1,200 Newton meters equals I times alpha. And then the I, of course, would be from our first part of the problem. So that would give us our 560. Let's just put that in there. 560 kilograms times meters squared times alpha. Okay, and then finally my this alpha is going to be used to find my, I'm going to put in the time that they give me. They say for 3 seconds. 3 seconds. You assume that the initial speed is 0, and so you can find that. Okay, so you're going to report that, that angular velocity at the end of the push. Okay, so we used our forces to find our angular velocity, which helps us to find our final speed. Now, for the third part of the problem, we're going to use the conservation of angular momentum. Okay, so we found this speed in the part B. We know the moment of inertia in part B. So we can already calculate the initial angular momentum, which is I initial times omega initial. Now, the story is that our I is going to change. So our I final is going to be that moment of inertia of the merry-go-round, which is 500 kilograms times meters squared. But the position of the child has changed, so it's going to be the mass of the child, which, let's see, what was it? 15 kilograms. Whoops. 15 kilograms times the position. Now, instead of being out on the edge, the child is closer to the middle. So the moment of inertia is going down here, 1 meter squared. Okay, so instead of having 560 kilogram meters squared, you're having 515. So consequently, instead of having your I times omega staying the same, your I is going down, so your omega should be going up. Okay, so in part B, you're giving me that omega initial, and now the child has moved towards the center. This causes the merry-go-round to speed up, and there you go. All right, so that problem is a lot, but I think it's doable. All right, so now we're very close to the end of our video and of the class. Our last idea was universal gravitation. The idea was that every mass in the universe is pulling on every other mass. But how do they do it? Well, at least in sort of a simple classical way of thinking about it, we can think about it as the gravitational field is communicated by this gravitational force. And we will have much more to say about fields and forces next semester when we talk about the electromagnetic field. The other thing that we talked a lot about was how the gravitational force can act as a centripetal force on on satellites. And of course, the story here is that instead of it's not that the gravitational force becomes weak that allows this the object to orbit. It's that they're going fast, and they're going fast enough that the rate at which they are going forward is matched by the rate at which they're falling. So they continue to go around the circle. So the gravitational force is equal to the centripetal force. And so your G little m, that's the mass of your satellite, big M, that's the mass of the Earth in this case, over r squared, equals your centripetal force. So it's mass times, and if it's for circular motion, it would just be v squared over r. And that would give you, if you just clean it up a tiny bit, multiply both sides by r, divide both sides by little m, it would give you v equals square root of gm over r. And we use that to derive Kepler's law of periods. Okay, so to hit it again, where does that g come from? Where does that 9.8 come from? It comes from the mass of the Earth, the radius of the Earth, and you have to put them into your laws. So here, our force of gravity is gmm over r squared. R is the distance between the centers of masses of U and the Earth, in the case of G. So there's your force of gravity. And if that is used just on a falling object, that would be your net force, which Newton's second law, of course, gives us is just ma. So if we wanted to find out what that gravitational acceleration is, we could just set these two equal to each other. And ma equals gmm over r squared. Divide both sides by m, and immediately you have that your gravitational acceleration depends on the mass of the planet that you're near and how far you are from its center of mass. So, going back here, it says a rocket ship is coasting towards a planet. Its captain wishes to know the value of g at the surface of the planet. So you are not at the planet yet. You're somewhere far out, and you're coasting towards it. You're accelerating towards it. This may be inferred by measuring the apparent weight of one of the crew. No, sorry, that gives you g at the position where you're at. It doesn't give you g at the surface of the planet. Measuring the apparent weight of the object of known mass in the ship. Again, that gives you the value of g exactly where you're at. Measuring the diameter of the planet, I don't think so, because that doesn't tell you anything about the mass of the planet. Measuring the density of the planet. Again, that could be helpful if you had the also the diameter. If you had both of these things, you could make some progress. Or E, observing the ship's acceleration and correcting for the distance from the center of the planet. Ding, 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 ding. You could do something with this, because if you knew your distance from the planet and you knew your acceleration, then you could figure out what the mass was and calculate what your g would be at a different one. Okay, so that's kind of a maybe too conceptual question. Here's another equally tricky question. Again, a little too conceptual. I don't think I would put this on the exam, but it's interesting regardless. It says to measure the mass of a planet with the same radius as Earth. Okay, so I'm saying let's think of this planet as planet X, and the r of X equals the r of Earth. Drops an object from rest from an altitude of 1 radius above the surface. Okay, next it says when the object hits, its speed is 4 times what it would be if the same experiment were carried out for Earth. In units of mass of the Earth, the mass of the planet is. Okay, so what we're thinking about here is you're dropping a ball on Earth, and you're dropping this ball on planet X, and it says when the object hits, its speed is 4 times what it would be on Earth. Okay, so if you start out and you drop this is your v on Earth, and your v on planet X is going to be 4 times the v on planet Earth. Now, when I was making up this PowerPoint last night, I put this equation on because I said, okay, well, that's our basic one. But I think it's a little bit easier to see if you use a different equation. So v squared minus v naught. This is another one of our equations from our constant acceleration unit. So if we use this idea, you'll see, okay, how could we infer what the gravitational acceleration is from this? Well, if the distance is the same, okay, let's say we're dropping them from rest. If you have the v Earth squared equals 2 acceleration of Earth, on the other hand, your Vx is going to be 4 v Earth squared, would give you that 2, this is the same delta x, 2 times acceleration on planet X times delta x. Now, if you look at this, this gives you a factor of 16 different in the acceleration. So, if you have acceleration on Earth, g on Earth is going to be, it's 16 times the g on Earth is going to give you the g on planet X, because that's how much bigger the acceleration is going to be. If you're looking at this expression for the acceleration, what does it due to? It's due to g, the big G, that's a constant. Big G is just your 6.67 times 10 to the minus 11th newtons times meters squared over kilograms squared. So that's just a constant of nature, measurable. But here, this G is going to depend on how far you are away, and it's also going to depend on the mass of the planet. So if these are carried out with the same mass, it must mean that this planet X has a mass that is 16 times greater than the mass of the Earth. Okay, so that one I concede is a little tricky. I also want to remind you that we did a short answer question on gravity in a different video, and so I encourage you to make sure that you understand exactly how to do that before the exam. Okay, so that's the end of our semester. That's the end of this video. Thank you for watching. Thank you for all your hard work this semester. And reminder that if 6 more of you fill out your course evaluations and say things like, Cordall, amazing, loved his course, or Cordall, hated him, please fire him, get him off of the campus. Either one of those both will help to get 5% on everyone's exam score. Okay? So thanks for watching, and good luck studying.